Okay, so let's talk about diving medicine and the rate in which I onload or offload gas. I mean, if we're talking about the compression, so the gas can accumulate inside the tissue like nitrogen or get out. So in, for example, the compression stops, we want to get the nitrogen out without the nitrogen forming too many bubbles, so we won't get the compression sickness. So the question is, what is the rate according to the tissue in which the nitrogen is? What is the rate of releasing the nitrogen in decompression stops? You can also conclude what is the rate of onloading the gas, but I won't talk to it too much. It's just the opposite of what I'm going to say because it's, let's say, less important, because usually, not less important, but usually less useful. I don't know. Anyway, I'm going to talk mainly about the offloading, but it's the same for onloading, just change the values. Okay, so we have the formula for the tissue pressure of that gas. So the partial pressure in the tissue of the gas we're talking about, for example, nitrogen. By the way, this is the name of this formula, the Buhlmann style model from the Haladan model. So what is the partial pressure of the gas we want to talk about inside the tissue, um, according to the time? So it will be based on the half-life of the gas in that tissue, and based on the Haladan model, it is depends on which compartment we are talking about. There are the fast compartments like the brain, or there are the slow compartments like the fat, like the cartilage, like the tendons, like the bones, and both have different half-lives. So the K right over here is going to be changed. See that the K value is ln 2 divided by the T half of that tissue compartment. So it depends on the speed by which the gas is offload or onload in that compartment. So again, the partial pressure in the tissue of a gas based on time is the ambient pressure of the gas, and the ambient partial pressure of a gas is what is the fraction of the gas we're talking about, usually nitrogen or helium in the breathing gas, times the partial pressure of the ambient pressure we are at. For example, if you dive to 10 meters underwater, you are with partial pressure ambient of 2 atmospheres, because every 10 atmospheres is 10 meters in the water is 1 atmosphere, and another atmosphere for the surface, minus the partial pressure of the water at body temperature. You see this value, and you can calculate the P ambient pressure of gas. And look for a very important note that if we breathe only oxygen, like we sometimes do in decompression stops, so the fraction of nitrogen or helium becomes zero. So the, all this will become zero, and this will become zero, and that also will become zero. So if you only breathe oxygen and the decompression stops, what you usually do, it becomes a much simpler formula with only this times this. Okay, so let us just look at the full formula. So we talk about the partial ambient gas plus the partial pressure of the tissue at time zero when you start calculating, minus again the partial pressure of the ambient pressure of the gas, which is this again, the same value, times e to the power of minus k. We said what is the value of k depends on the half-life of the tissue compartment, times t, which is the time in minutes. Okay, so let's see an example of a washout when we will use oxygen as the breathing gas in a decompression stop. So we will look at depth of 6 meters. For example, it may be the decompression stop according to the US diving manual. The tissue half-life is 20 minutes, namely it's around a medium speed of compartment. We breathe air before switching. So you can see that the pressure of the ambient gas is like this. After a long time, we got to partial pressure of tissue of start, namely the PT0 would be 1.22 bar. Let's say that bar is like atmosphere for ours, for our case. Now in the decompression stop, we switch to O2, so the partial pressure of the atmosphere gas is zero. So this will become zero, and this will become zero. We'll be left only with the starting partial pressure we saw times this one, which will be equal to this one. So we get this formula with those zeros because we're breathing oxygen. So peak tissue of the gas, in this case nitrogen, equals the starting partial pressure. We had a starting partial pressure of 1.22 bar times e to the minus ln 2 divided by the half-life of the compartment. We said it's 20 minutes times the time we are waiting in the compression stop. For example, if we wait 20 minutes, so we'll get this value. Namely, we reduced the partial pressure of the gas in this tissue to 0.61 bars because we did a decompression stop at 6 meters using oxygen 20 minutes. Of course, if we didn't use the oxygen and instead used air, this will be much higher than zero, and you will get a number that is much higher. This is why decompression stop with oxygen is much more efficient than decompression stop with air, for example. Just think about it. If you breathe air instead of oxygen, this value, this ambient pressure would matter inert. It will be, they even calculated this. You see right over here, they calculated this value 1.22 bar. No, okay, they didn't calculate it. Okay, they did. Okay, they just said that we are getting to a equilibrium. Anyway, if we breathe air, yes, it's in 1.6 bar, so it's in 6 meters. If we used air instead of oxygen, the value right over here was 1.22 bars, and here also 1.22 bars, so it will be 0, and this will be 1.22 bar, and as you can expect, nothing will happen. So because we got to a saturation here. So I'm not sure that it's the best example, but just show you how breathing oxygen makes the offloading of gas from the tissue much more efficient. And that's it. This was about the, let's call it, onloading, and in this case I use it for offloading gas, the Buhlmann style model from the Haladan model for, let's call it, change of partial pressure of gas in the tissue. Of course, we're talking about nitrogen and helium because they are the gas that are most relevant. They are inert gas, so they are relevant for decompression sickness. Okay, thank you very much. We saw an example, and now we can take this partial pressure and see, compare it to the M value, see if it's lower than the M value in the surface, and if it is, we can get to the surface based on the model for decompression sickness. You know, comparing the partial pressure of the tissue to M value can help you understand until where you can ascend without forming bubbles according to Haladan model and its upgrades. Thank you very much. If there are any mistakes or corrections, please tell me. This was about the formula for gas offloading and onloading in decompression sickness. And that's it for now. Thank you very much.